Hello everyone. Today we are going to see about forward propagation. Forward propagation in neural networks. According to universal approximation theorem, a well-guided and engineered deep neural network can approximate any arbitrary complex and continuous relationship among the variables. In fact, there are several other reasons behind the success of deep learning. A neural network is a series of algorithms that endeavors to recognize underlying relationships in a set of data through a process that mimics the way the human brain operates. As the name suggests, the input data is fed in the forward direction through the framework. Each hidden layer accepts the input data, processes it as per the activation function, and passes to the successive layer. In order to generate some output, the input data should be fed in the forward direction only. The data should not flow in the reverse direction during output generation, otherwise it would form a cycle and the output could never be generated. Such network configurations are known as feed-forward network. The feed-forward network helps in forward propagation. At each neuron in a hidden output layer, the processing happens in two steps, pre-activation and activation. Pre-activation. It is a weighted sum of inputs, that is the linear transformation of weights right to inputs available. Based on the aggregated sum and activation function, the neuron makes a decision whether to pass this information further or not. Activation. The calculated weighted sum of inputs is passed to the activation function. An activation function is a mathematical function which adds nonlinearity to the network. There are four commonly used and popular activation functions: sigmoid, hyperbolic, tangent, ReLU, and softmax. In the example, we will be using a three-layer network. The network and parameters can be represented as follows. Let us say that we want to train this neural network to predict whether the market will go up or down. For this, we assign two classes, class 0 and class 1. Here, class 0 indicates the data point where the market closes down. And conversely, class 1 indicates that the market closes up. To make this prediction, a trained data X consists of two features, X1 and X2. Here, X1 represents the correlation between the close prices and the 10-day simple moving average of close prices. And X2 refers to the difference between the close price and the 10-day SMA. In this example below, the data point belongs to the class 1. The mathematical representation of the input data is as x is equal to matrix of x1, x2, 0.85, 0.25, y is equal to 1. Example with two data point is given below. The output of the model is categorical or a discrete number. We need to convert this output data also into a matrix form. This enables the model to predict the probability of a data point belonging to different classes. When we make this matrix conversion, column represent the classes to which the example belongs and the row represent each of the input examples. Y is equal to y1, y2, 0, 1, 0, 1 is the matrix form. In the matrix Y, the first column represents the class 0 and the second column represents the class 1. Since our example belongs to class 1, we have 1 in the second column and 0 in the first. Here you can see the diagram class 0 and class 1. This process of converting discrete or categorical classes to logical vectors or matrices is called one-hot encoding. It's sort of like converting a decimal system to binary. We use one-hot encoding as the neural network cannot operate on labeled data directly. They require all input variables and output variables to be numeric. In a neural network learning, apart from the input variable, we add a bias term to every layer other than the output layer. This bias term is a constant mostly initialized to 1. The bias enables moving the activation threshold among x-axis. When the bias is negative, the movement is made to the right side, and when the bias is positive, the movement is made to the left side. So the biased neuron should be capable of learning even such input vectors that an unbiased neuron is not able to learn. In the data set X introduce the bias, we add a new column denoted by ones as shown below. Here you can see the values. Let us randomly initialize the weights or parameters for each of the neurons in the first layer. As you can see this diagram, we have a line connecting each of the cells in the first layer or to neurons in the second layer. This gives us a total of 6 weights to be initialized. 3 of each neuron in the hidden layer. We represent these weights as shown below. You can see here see theta 1 and theta 1 value. Here theta 1 is the weight matrix corresponding to the first layer. The first The first row in the above representation shows the weight corresponding to the first neuron in the second layer, and the second row represents the weight corresponding to the second neuron in the second layer. Now let's do the fourth step of the forward propagation by multiplying the input value of each example by their corresponding weights, which is mathematically shown below. Here the equation is theta 1 into x. Before we go ahead and multiply, we must remember that when you do matrix multiplications, each element of the product x into theta is the dot product sum of the row in the first matrix x with each of the columns of the second matrix theta 1. When we multiply the two matrices x and theta 1, we are expected to multiply the weights with the corresponding input example values. This means we need to transpose the matrix of example input data x. So the matrix will be multiply each weight with the corresponding input correctly. Let us see how the neural network looks like after the addition of the bias unit. Here you can see the diagram. Before we run our matrix multiplication to complete the final output z cube, remember that before in z square calculation we had to transpose the input data a1 to make it correctly for the matrix multiplication to result in the computation we wanted. Here our matrices are already lined up in the way we want, so there is no need to take the transpose of A square matrix. Now let us perform the matrix multiplication. Here we are performing matrix multiplication. Z cube is equal to theta 2 into A square, where Z cube is the output of the matrix before the application of an activation function. As you can see, the probability of example belonging to the class 1 is lesser than class 0, which is incorrect and need to be improved. Thus, we have not only understood the basic structure of neuron, but also a neural network. Further, we took a look at forward propagation in neural network with the help of an example. Thank you.